The market seems to be flooded with a lot of these all-in-one pocket oscilloscopes that have function generators, oscilloscopes, and in this case it has a transistor diode tester all built in. Are these things any good? Quite frankly, I don't think so. But for hobbyists, they might do the job. Anyone who's serious about electronics really needs to get proper test equipment. This just doesn't cut it. I'll show you why. It can do some things, but it can't do everything. And we'll see why in a minute. Let's check it out. Today we're going to look at this new multifunctional transistor oscilloscope. This one's the DSO TC4, and they call it a multifunction transistor oscilloscope. Okay, let's take a look at this. It's an oscilloscope. Basically, it's a oscilloscope, signal generator, transistor tester, and has 13 waveform outputs. So it's a multifunction. You can see transistors will plug right into the front here, and it'll check transistors for operation and gain, I'm sure, everything. Let's open it up and kind of go through it and see what it does, and then we'll fire it up and test it out. Open it up. It's still factory sealed. Comes with a destruction manual, the unit itself, probe and adapters. Inside the Ziploc bag. Got an adapter. This is for the signal generator. Okay, that's actually for everything. It's a BNC adapter for everything. DSO, DDS, and in 0 to 40. It's interesting they only have one. So if you're going to use it as a scope, you would put your scope probe on. You have to put your scope probe on first and then plug it in. The signal generator will plug in directly with clips, USB charging cable, identifying rings and clips, and an adjustment tool for calibrating the probe. Just get your standard 1 and 10 times probe. To power it up, press the power button. I don't know what kind of a charge is on the battery, but I'm sure it's got some juice in it. And I want to select English, I guess. I don't know how to do this. Down. There we go. English. Okay. Okay, so now in transistor test mode, oscilloscope, signal source, toolbox, settings. Those are the modes. That's for changing your signal source. You can generate waveforms. We'll look at this on my other scope. That's transistor test. That's for selecting the signal that you want to produce. So it's a 1 kilohertz now to go up to 50 kilohertz. That's as high as it'll go as 50 kilohertz. And 1 hertz is the lowest. There's the oscilloscope. It is displaying video, color bars to be exact, and as you can see, it's well, it's not doing a very good job, but I didn't expect it to. It's a digital scope after all, and these cheap digital scopes, it's also only got 10 megahertz of bandwidth, so looking at complex waveforms such as video, not going to work. It's also completely useless for looking at the RF output from a video machine, and that's what we're looking at here. We're looking at the output, the RF out from my 3/4 inch deck that's got play in the background. I can roll the tracking, nothing happens there. I'll show you the other scope. I'll show you the TV as well. I've got the video. You've heard the music playing, I'm sure, from the from one of my tapes. So this is the tape that's playing on the 3/4 deck. I can roll the tracking. Right. This is a new recording on an old tape. One of those old tapes that had nothing on it, that had self-erased itself just from sitting. I recorded a new recording on it, and it plays fine. Okay, it plays perfect. But the signal coming off the scope is, well, it's not there. But if we look on the other scope, I've got both of them hooked up at the same time. You can see that the waveform on the RF is there. And if I roll the tracking, actually not bad considering this video machine is one I just slapped a head on and didn't even do an alignment. This is the one that I changed the head on. I didn't even do an alignment, and it's pretty damn close to being perfect. So as far as using one of these little handheld scopes for doing VCR, and I would even imagine a DVD player alignment, no, they're not going to do it. For displaying audio signals, obviously it's going to be able to display them a little easier, although it is, being a digital scope, you're just looking at one little snapshot, so it's refreshing every, what, half a second, every 1/4 of a second it gets here. It's doing four refreshes per second at this scan rate, which is 5 milliseconds. And I can, of course, increase the scan rate. And now we're seeing a 200 microsecond capture. And of course you can stop it, freeze your waveform. Now these are better for obviously capturing digital logic. For example, if you're reading an output from a memory dump, for example, this would display it. You could set it to capture and capture just one event. And that's what digital scopes I find are better for, and that's why I don't really use them. I have the Unity digital scope here that I bought, and I paid a lot of money for it. And I found that, well, I bought it when my Watsu scope took a dive, when the tripler went out on that. I went and bought a Unity, and I spent like 500 bucks on it. Got it home and realized it was not what I was looking for. Went back to the shop and they said, sorry man, all sales are final. Even though the salesman, which obviously knew nothing, assured me that, oh yeah, it's got 100, it was 100 megahertz, 1 gig of sample, and it was going to capture video perfectly, and it does about as good a job at capturing video and RF output from CD players and VCRs about as well as this one does, which means it doesn't. That's why I had to get another analog scope. I got the Tektronix for that reason, because when you're working on analog electronics, which is really all that I work on, it's you need an analog scope. Unless you go really, really, really high end. I understand that the DSOs, that they're really, really expensive, like the Tektronix ones that are thousands upon thousands of dollars, they can do a very good job. But these basic scopes, forget it. It's that. It's okay for looking at lower waveforms, audio, maybe some of the IF stages in radios for example. It worked fine for that. It'll even tell you what frequency we've got here, right? It's telling me the frequency as it's jumping around. Depending on what you're servicing, a little scope like this might be useful. Next, we're going to look at the function generator, and I'm going to show you the scope. This is not what I expect to see for a sine wave. In this aspect, this kind of is a fail. I don't think our sine wave should be made up of these little dots. Like, the resolution certainly isn't very good. You can see it steps as it's producing the sine wave. I think it should be a lot cleaner than that. My other function generators produced a perfect sine wave, but this one is not. This is the amplitude is 3 volts. I can turn the output down. This is 60 hertz we're looking at now. Again, yeah, it's kind of rough, and as I increase the frequency, 100 hertz, 200, 300, 400. This is 1 kilohertz. $1,500, 2 kilohertz. It's getting better as the frequency goes up. There's 2 kilohertz. We get to, there's 4 kilohertz now. The steps aren't quite as noticeable on the higher frequencies as the lower frequencies. We'll go to 5 kilohertz, 6, 7, 8, 9, 10 kilohertz. That's getting better. You know, as we get into the higher frequencies, the stepping is a lot less. That's 20 kilohertz. $30 kilohertz. 40 kilohertz. And that's 50 kilohertz, which is the maximum it goes. If I try to change it, it'll probably go to nothing. Yeah, it won't go any higher than 50. 40, 30, 20, 10, 9, 8, 7, 6, go all the way down. As you can see, we're starting to get at 1 kilohertz, we're starting to pick up those stepping. 900 hertz, 800. And then I'll go down. 90, 80, 70, 60, 50, 40, 30, 20, 10 hertz. We can go down to the single now. 9, 8, 7, 6, 6 hertz, 5, 4, 3, and go right down to 1 hertz. There's 2 hertz and 1 hertz. You can also display square waves. We're looking at 400 hertz square wave, and that signal looks to be pretty good. They call this one the sawtooth, but actually this to me looks more like a triangle wave. Half wave, full wave. This would be what you would see from a rectifier, full wave rectifier from AC. This one's a step wave, reverse step, index up, index decrease. Yeah, we're at 50% here, but I can change that duty cycle from 10%. Actually, you can go down probably as low as 1%. Yeah, 1% all the way up to 99%. We're at 50% there. I'll go by 10, 60, 70, 80, 90. And 100% obviously is DC. You can also change the duty cycle on the sawtooth. That's more like what I would call a sawtooth. Or that. So there's your sawtooth at 100% duty cycle. That's what you would find like for the vertical output for a television. There's a signal looking more like that. Sawtooth at 50% is a triangle wave. And then reverse sawtooth. This one's called a multi-audio signal. This is a sync pulse, Lorentz waves, and then back to sine wave. So these are the different waveforms it can produce. Next is the transistor tester. I have a couple bins of some very old and obsolete transistors. I don't know whether they work or not, but we'll plug them in here and just see what happens. This one's a 2N5294, I believe. We just pop it in there and test in progress. Tells you what you need to know. So pin 1 is the base, pin 2 is the collector, pin 3 is the emitter, and it gives you the gain. HFE is 0, IR is 5.9 milliamps, and the UBE is 509 millivolts. That's that one. If I grab another transistor, again, don't know anything about it. Oh, that one, the leads are kind of buggered up on. Let's see if this one will go in. What is this one? Well, we'll find out. We'll just pop this one in here somehow and close the gate, and will it run it? So this is an Audion, as they call it, PNP transistor. Pin 3 is the collector, pin 2 is the base, and pin 1 is the emitter. So it's EBC, basing the way it's stuck in there. This one has an HFE or gain of 67, IR 706 microamps, and UBE is 147 millivolts on this one. What is this one going to show me? It's a PNP. Pin number 1 is the base, pin number 3 is the collector, and pin number 2 is emitter. And because the pins are so wide spaced, you'll see that that pin 1 is over here, and then the next one over is into pin 3, and then this one's into pin 2. So that's telling me it's base, collector, emitter. It's an audio transistors, NPN. Gain is 18, 509 millivolts between the base and emitter, and 6 milliamps. Here's another unknown transistor. Another audio. This is a PNP. Gives you the specifications. Tells you that right there, PNP. It's an NPN transistor. Gain on this one's quite high, 396. The measure, this is a diode, right? The cathode is on the green one here, right? And the cathode is plugged into pin number 3. Toolbox. Now this is where we can do other tests. The input here on the top, it's got a 0 to 40 input. If we plug our test leads in, if I measure, for example, a battery, it will tell me that this battery is 4.2 volts. What happens if I reverse it? It should say negative 4.2. Does it? Or will it not? Is it smart enough to know negative voltages? Come on, probes. It doesn't. It has to be the correct polarity. But you can measure 0 to 40 volts. So if I turn on my power supply, so it's got a basic voltmeter. Power supply is set for 3.1. If I clip it on, it's going to measure 3.1 volts. 3.2. And this will go all the way up to 40 volts. So I can crank this thing all the way up to its maximum output of 32.4 volts. So you can measure voltage with it. Zener diode. If I press the Zener diode mode and I place a Zener diode in the cathode and anode positions on here, that's where these work. Couldn't figure out why I couldn't get it to work before, because it's in here. It's in this setup. This is a 5.1 volt Zener. It's actually measuring 4.46 volts. I could grab another Zener diode here. Let's what's this? This is another one that's 5 volts. I do have others in here. We'll just check some other ones. I know I've got a few others in here of different voltages. And this one here should be a little higher voltage. So we'll just test this one. That's an 18 volt Zener. So it does test the voltage of Zener diodes. So if you've got a bag of Zener diodes kicking around and you don't have them labeled, this will help you sort through your different voltages of Zener diodes. The on-off test is for testing the functionality of the transistor tester, just for opens or shorts. That's for testing it. I clip the leads together. It's measuring resistance. The other settings here, the DS18B20 and the DHT11, they are for single wire digital temperature sensor measurement and the digital temperature humidity sensor measurement. So if you've got a humidity and temperature sensor, you could check that on DHT11, or a single wire digital temperature sensor using a DS18B20. That's what those modes are for. That's it. Throw a link in the description. Again, this is a hobbyist type unit. I wouldn't be using it for diagnostic work, that's for sure. It's not accurate enough, but for your average hobbyist, this might do the job for you. Thanks for watching.